Over the last several days, we've taken a look at the photoelectric effect, which says when light strikes a piece of metal or some other material, but usually a metal, sometimes an electron is ejected, right? The electron gains energy from the photon. It moves up to a higher level, and eventually, if it has enough energy, it leaves the atom, forms an electric current. Well, Arthur Compton discovered something that was kind of similar to the photoelectric effect, but was a little bit more than the photoelectric effect. He noticed that when light strikes a piece of metal, light that is of a really, really high frequency / high energy, like X-rays, strikes a metal, an electron can be ejected, yes, but sometimes a second photon is ejected as well. So you've got the original photon striking the metal, the electron is ejected just like it was in the photoelectric effect, but now there's also another photon that's ejected as well. Now we noticed that that second photon was less energetic than the first photon, which was a little bit odd. It's a little bit odd. When you're running hard, okay, you're running hard against say a group of people. There's a whole group of people that are kind of off in the corner over here, and you run really, really hard at them. Okay, and you run so hard at them that when you bump into them, one of those people bounces off. One of those people leaves, and then you bounce off. Okay, you're not less energetic than you were when you hit it. Okay, you're the same person you were when you hit this group. So you would think, at least, if there was going to be a second photon that was ejected here, that second photon would be the exact same thing as the first photon. Okay, the first photon strikes the metal and the electron's ejected, but the first photon just bounces off. But that's not the case. The photon that bounces off is less energetic than the first. Classical theory, which is about pre-1900-ish theory, predicted that a photon was emitted. It should have the same frequency and the same energy as the first X-ray, the first photon. In other words, if a single photon hit this and caused an electron to be ejected, and there was another photon, and there was a photon that came off of it, it should be exactly the same thing as the first photon. Just like when you bounce off of that group of people, you're not bouncing off different than you were before. You're the same person you were when you struck that group of people in the corner. Now, Arthur Compton explained this by proposing that photons have not only energy. Einstein established that. Einstein said photons have an energy that's equal to h times f. But he also said, Compton that is, also said that photons have momentum. And that this whole thing, this whole Compton effect where there was an electron ejected and a second less energetic photon ejected, was really just a collision. And collisions, we know way back, the beginning of September, we can analyze them by the law of conservation of momentum. So it's really just a collision in which photons have momentum, and we can analyze the collision with the law of conservation of momentum. Now, just a couple of little terms here. The scattering of the photon is called Compton scattering. The change in energy of the photon, the decrease in energy of the photon, is the actual effect that we call the Compton effect. I wouldn't lose any sleep over those two terms, to be honest, just to distinguish kind of the intricacies of it here. So what's so special about this? Sometimes we're guilty of just writing without thinking about what we're writing. What's so special about this? Photons have energy. That's not new. E is equal to hf equals hc over lambda. Einstein proposed that in 1905, and it's pretty well established. The idea that photons have momentum is new, and that's really, really odd. It's even odder than the idea that photons have an energy. It's odder because momentum, we learned back in Unit 1, is equal to m times v. But photons don't have any mass. If the mass is zero, how can we have momentum? That's the big question. If the mass is zero, how can we have momentum? Compton said we have to. That's what explains this whole phenomenon called the Compton Effect. But how can they have momentum when the mass is 0? Well, let's write down that equation for momentum that we learned back in Unit 1. P is equal to m times v. Momentum is equal to mass times velocity. But remember, the whole problem, the whole conflict that seems to exist here is that photons don't have any mass. Let's go back to Einstein again. Einstein's rearing his head quite often now, the last little while, and will continue to pop up over the next couple weeks. I mean, Einstein is post-1900 physics, right? Along with something called quantum theory that Einstein kind of helped invent, but didn't really have much to do with after that. Along with quantum theory, Einstein is is the biggest name in physics post near the year 1900. Einstein said, you guys have probably heard this before, to some level, but not really understood it. Einstein said that if photons don't have any mass, but photons have energy, and energy and mass are two different forms of the same thing. What does that mean? Energy and mass are two different forms of the same thing. Well, ice and steam are two different forms of the same thing, right? They're both chemically water, right? You can change ice to steam, and you can change steam to ice. They're not exact, they don't look the same, they don't feel the same, but they're two different forms of the same thing. Similarly, not exactly the same because it's not a chemical thing, but similarly, energy and matter are two different forms, or energy and mass are two different forms of the same thing. And you can change energy to mass, and you can change mass to energy. They're two different forms of the same thing. Now, we have to have a way to relate energy to mass mathematically if they're two different forms of the same thing. This is what I guarantee you've seen before, but probably not really understood. It is probably the most famous physics equation ever, and probably one of the least understood physics equations ever. Anybody know what it is? It's the equation that relates energy to its equivalent mass. E equals mc squared. So Compton said, yeah, look, photons have momentum equal to m times v, but there's no mass. Einstein said, yeah, there's no mass, but there's an energy, and therefore there's an equivalent mass. They don't have any mass, but they have energy that's equivalent to this much mass. So let's sub in E over c squared for the mass times v. Oh, but wait, v is the speed of the photon, which is just c. So that cancels. So we're left with P is equal to E over c. On your data sheet in the top right-hand corner, that appears in this form. E is equal to P times c. The energy of a photon is related to its momentum and the speed of light. So all of a sudden now we have an equation that describes the momentum of a photon without referencing the mass, because there is no mass. Get rid of the squared because it's c over c squared. It'd be like saying 2 over 2 squared, right? Same as 2 over 4, right? So one of them cancels, right? Does that make sense? You don't have to derive that equation anyways, okay? Because in the end, that equation is on your data sheet. I just wanted to show you that it comes from somewhere, right? The meaning of that equation. So now we've established that, yeah, look, if Einstein's right about this whole energy mass equivalence thing, then maybe Compton's right too. Maybe this whole idea that photons have momentum and it's just a collision between the photon and the electron and blah, blah, blah. Maybe that's good. Maybe that works. It seems to explain the whole Compton effect. Maybe it's valid. Maybe it's correct. All right, so there's one equation. Now you're going to see another equation in the top right-hand corner of your data sheet. It looks like this. E is equal to hf. Well, we can replace E with h times f. We can also see another one that says P is equal to h over lambda, because in the end, we can say hc over lambda is the energy. Divide that by c, c's cancel. I'm left with P is equal to h over lambda. So you're going to see all three of these equations valid for the Compton effect. All three of these equations that describe a relationship between the momentum of a photon and either the energy of the photon, the frequency of the photon, or the wavelength of the photon. Notice in all three of these equations, conspicuously absent is the term mass. Mass doesn't appear anywhere. Now, don't change anything you've learned to this point. If you're asked to find the momentum of a car, use m times v. If you're asked to find the momentum of a proton, use m times v. If you're asked to find the momentum of a photon, use one of these three equations. Yep? Use what? Sorry, E is equal to... say it again. Yeah. Oh, sorry, no. So what are you saying? Impulse, F times T? Yeah, okay, go ahead. No? Did you answer your question in your mind, or are you just kind of abandoning it? You answered it? Okay, okay. Because I want you to understand it. I'm not completely understanding what you're asking, but I want you to ask the question if you still don't understand what you're... You sure? Okay. Okay, now there's another one as well. The good news is I'm not going to ask you to derive this equation for sure, mainly because I can't remember how to derive it myself. We don't have to derive any of these. I just wanted to show you where the first three came from. This looks like an ugly one. It's not as bad as it seems, actually. Comes from the law of conservation of energy and the law of conservation of momentum. What it says is that delta lambda, which is the change in wavelength. Look, if the energy of the photon changes, then the wavelength of the photon will also change. It's equal to lambda f minus lambda I. Hey, by the way, if the energy decreases, what's going to happen to the wavelength? Decrease or increase? If the photon goes from, say, an X-ray to ultraviolet because the energy is decreased, the wavelength will increase. So you're going to have a decrease in energy. You're going to have an increase in lambda. It's equal to lambda f minus lambda I, but it's also equal to h, which is Planck's constant. We're always going to use for this one the 6.63 value of Planck's constant, over m. Simon, you know the answer to this. What m do we use there? I'm asking you because I know you know the answer to this. Mass of what? Yes. Okay, we're talking about the mass of the electron now, which will always be 9.11 times 10 to the minus 31 kilograms. So we're not going to replace that mass with an equivalent mass or anything like that, because we're talking about not the mass or the equivalent mass of the photon, but in that instance, we're talking about the mass of the electron, which we don't have to replace with an equivalent mass because it already has mass. C is the speed of light, 3 times 10 to the 8 meters per second. Theta, oh, everybody gets this, right? It's the angle. What angle? It's the scattering angle of the photon, of the X-ray, in degrees. So h over mc times bracket 1 minus cosine theta equals delta lambda. You could say it seems ugly, but once you go to do it, it's actually not so bad. It really isn't. So what do we got now? Boy, some new equations here today. We've got E is equal to P times C. We've got P is equal to HF over and we've got P is equal to H over lambda. In addition, we get this nice new fancy equation, H over MC times 1 minus cosine theta. Let's take a look at a couple examples here. First one says, calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. Okay, this is a straightforward question. The energy of the photon is the easiest part of it. E is equal to hc over lambda. I'll tell you what, when we go to do this question on a test, some of you get it wrong. Some of you mess up on calculating the energy of the photon. After we go over the Compton effect and photon momentum, too many of you start thinking making this question too complicated. You're asked for the energy of a photon. You could have been asked for the energy of a photon a week ago and still easily solve that problem. E is equal to hc over lambda. Don't make it harder than it has to be. If you want to get it in joules, then we're going to say 6.63 times 10 to the minus 34 joule seconds times 3 times 10 to the 8 divided by 600 times 10 to the minus 9. We get 3.315 or 3.32. Let's write down the unrounded number, actually. 3.315 times 10 to the minus 19 joules, which is 3.32, rounded to the right number of digits, times 10 to the minus 19 joules. All right, you want to find the momentum? You got a couple of options here now to find the momentum. Here's my equations. Okay, here's my equations that involve momentum of photons. Which one do you want to try here? Yep. P is equal to h over lambda will work just fine. What else could you try? Given what you have already in this question. P is equal to h over lambda is probably the one I'd use too, Maria, and we will use that one. But remember that you could also use, Devin. Yeah, use the first one as well, equals PC, because you just solve for E, right? And you're looking for momentum, right? So you could use that one. I'd probably go with that one too, Maria, because that goes back to original data. If I made a mistake with the energy, well, then I'm not going to make a mistake with momentum here. If I go to this equation, then I will. Okay? So let's go P is equal to h over lambda. We're always, for these momentum questions, going to use the 6.63 value. Divide that by the wavelength 600 times 10 to the minus 9. We end up getting 1.11 times 10 to the minus 27 units. Oh, this is odd. Momentum, kilograms meters per second. Or you could say Newton seconds. Kilograms meters per second when we don't have any mass? The units for momentum. Remember, we don't have mass, but we do have equivalent mass, which is the same thing as mass, just another form of mass. So there's not really any issue with using kilograms there. I'll give you a couple minutes to work on these three questions, please. Let's have a look at number 3 here, guys. This is an energy question, not a momentum question, but it's probably the hardest of the three, I think. We want to find the energy that's gained by this electron. Let's think about that. Okay, let's think about that for a second. We don't actually have a way of directly calculating the energy gained by the electron. We haven't learned anything about the electron per se. We've learned about the scattered photon. The photon loses energy. It decreases in energy, it increases in wavelength. But if we can find the energy that's lost by the photon, wouldn't it be reasonable to assume that that's the same as the energy that's gained by the electron? The electron has to get its energy from somewhere. It gets it from the energy of the photon that's lost. So let's get the energy lost by the photon, and then let's say that's the same as the energy that's gained by the electron. We know that E is equal to hc over lambda. So wouldn't it be reasonable to say that delta E is equal to hc over delta lambda? Anybody try that? Okay, good, because that doesn't work. You can't see, you can say E is equal to hc over lambda, but you can't say delta E is equal to hc over delta lambda, because lambda is on the bottom. If lambda was on the top, like E is equal to hf, you could say delta E is equal to h times delta f. That would work. Okay, this doesn't. F and E are directly related to each other, so that works. If E and lambda are not directly related to each other, that doesn't work. So how are we going to find the change in energy? Well, let's get the energy initial by hc over lambda. Let's get the energy final by hc over lambda. And then let's say delta E is equal to EF minus EI. Right? That's going to give me a negative delta E. I don't know what its value is. I guess 1.8 times 10 to the negative 18 joules. That's the energy that's lost by the photon, the energy gained by the electron would be positive 1.8 times 10 to the negative 18. Right? Let's try another one. This one says, oh, get an angle. This is one of those ones with that ugly equation, isn't it? An X-ray photon of wavelength 0.05 nanometers scatters at an angle of 30 degrees. What's the wavelength of the scattered photon? This would be lambda I, right? The initial wavelength, and this would be theta. We're looking for lambda F. Well, we know that delta lambda is equal to h over mc, and I don't expect you to memorize this equation, obviously. Just check your data sheet for it. Times 1 minus cosine theta. We get 6.63 times 10 to the minus 34. This is one that I've never really understood why, because those three numbers in front there are always the same. Why we don't just have a single constant that replaces those three numbers. I've never understood that. Life would be not easier for us, but so much quicker for us than to have to write that out every time and to type those three numbers into our calculator. But it is what it is. 1 minus cosine 30 degrees. Let's figure this out. I'll pull out my calculator for this one. Let's get that coefficient. We get 6.63 times 10 to the minus 34. Divide it by, let's use some brackets on the bottom, 9.11 times 10 to the minus 31 times 3 times 10 to the 8. Okay, so my coefficient out front is 2.4 times 10 to the minus 12. Let's multiply that by, make sure you use brackets here, 1 minus cosine 30. We got to end the bracket for the angle. We got to end the bracket for the 1 minus cosine 30. See what I've done there? Is that okay for the calculator? We get 3.25 times 10 to the minus 13. Unfortunately, that's not the answer. But the answer is pretty easy to get now. What do you think I'm going to do at this point? What have I just found? What have I solved for in this question so far? Sorry? Not EF. Yeah, lambda F. What do I want? No, I haven't solved for lambda F, actually. I've solved for delta lambda. What do I want? Lambda F, right? So let's say delta lambda is equal to lambda F minus lambda I. Lambda F is going to be equal to delta lambda plus lambda I. So whatever we got there, 3.25 times 10 to the minus 13 plus 0.05 times 10 to the minus 9. Okay, add those two numbers up, and whatever we get is our answer there. I'm going to leave you with a question on page 724 for homework. In addition, I want to leave you with worksheet number 21, but not all the questions. I want you to do number 1 to 10. You're going to find the first 9 questions are really quick, like those questions you were just working on a few minutes ago, like one simple equation. The 10th problem is going to be like this, where you have to use that delta lambda is equal to h over mc times whatever. It's still not that bad, but it's a little bit longer than the first one. So this should take you maybe 15, 20 minutes. Okay, if it's taking you longer than that, it's probably taking you too long. Come and see me for some help on that. Okay.